Hello everyone. Today we'll be talking about phase change diagrams. What's a phase change diagram, you ask? And why is it important? Why do I need to learn about it? Well, a phase change diagram is a very useful and kind of universal tool that scientists can use to tell a story about what happens to a substance as heat energy was added to it and its temperature changed. It's a very common tool in a physics or chemistry class, so you should become familiar with it so that you can solve problems more easily. In this case, I'm going to make a phase change diagram that tells a story about an ice cube that receives some energy from its environment and heats up as a result. So here's our very cold ice cube. Brr. Because this is an ice cube, and therefore it's made out of water, or H2O, there are two very important temperatures in degrees Celsius that we should label on the y-axis of this graph. The two important temperatures are 0 degrees Celsius and 100 degrees Celsius. 0 is the melting point of ice, or the freezing point of water, and 100 degrees is the boiling point of water, or the condensation point of steam. So those are the two most important temperatures to consider. So let's begin our story. Someone lights a fire underneath this ice cube. Oh no! But don't worry, the ice cube cannot be destroyed, it can only change its form. So let's track that as it happens. On the x-axis of this graph, you'll see that it's labeled heat energy input. Well, we're actually adding heat energy to the ice cube right now. So as this event occurs, we should be able to move forward on the x-axis. But what's going to happen as we add heat energy? Well, the temperature of the ice cube will increase. So according to the way this graph is set up, as we go forward on the x-axis, we should also go forward on the y-axis. So the beginning of our story looks like this. So the ice cube will go from a very cold block of ice to a slightly warmer block of ice. Maybe it starts out at a negative temperature, like negative 50 degrees Celsius, and we've heated it up until it reaches 0 degrees Celsius. And what happens afterward? Well, what just happened now is that the solid was heating up. Makes sense, because we added heat energy to it, so its temperature increased. What will happen next if we continue to add heat energy? Will it go from 0 degrees Celsius to 10, to 20, all the way up to 100 and beyond? Well, actually, no. You might be surprised to learn that if we continue to add more heat energy after this point, we will actually not see a temperature increase. Instead, our graph will plateau, which means to go flat for a while. So we'll keep adding heat energy, and we'll keep adding heat energy, and we'll keep adding heat energy, and yet there will be no increase in temperature for a little while. Scientists, I assume, were baffled when they first started tracking these things and noticed that adding more energy did not increase the temperature of things like ice. And what they eventually realized is that there was some extra kind of energy that you needed to add in order to make a phase change occur. So that's actually what's happening, is the particles inside of the block of ice are changing from solid into liquid. So this is the part of the graph that shows the solid melting. Now, at the beginning of this plateau, all of the block of ice is solid, but by the end of this line, all of the block of ice has converted into a puddle of water. So now it's all liquid. So on the left is all solid, on the right is all liquid. But you'll notice it's the same temperature throughout that whole process. The heat energy in part 1 of this graph caused the temperature of the individual molecules to increase. They were vibrating more, so they had a higher temperature. But the heat energy in part 2 of this graph was doing a different job. It was taking the molecules and breaking apart the bonds between them so that as a liquid, the molecules can slide past each other more easily. So, what happens once all of the molecules are liquid? Well, at that point, you have 0 degree liquid water. So then if you add more heat energy at that point, going farther on the x-axis, then the liquid can start to heat up again, like before. So we get this next part of the graph that's going up like this until we reach 100 degrees Celsius. What's going to happen at that point? Well, you could probably guess that something similar to before is going to occur. Before the temperature of this water can rise above 100, it first needs to be boiled and converted into steam, or gas, or vapor. And that takes extra energy, just like melting took extra energy. So at the beginning of this new plateau, we have 100 degree liquid water, and by the end of this plateau, we have 100 degree steam, all in gas form. And this flat section of the graph here shows the transition between those two states, between all liquid and all gas. Once all of the liquid water has become all gas, then the temperature can exceed 100 degrees and go higher than the boiling point, and at that point the gas can heat up. And this is where we're ending the graph because it's not very interesting after this. The gas can just keep getting hotter and hotter and hotter until it eventually becomes a plasma and the molecules rip themselves to pieces, at which point this type of graph becomes meaningless. So we'll just stick with solid, liquid, and gas for now. Now remember that this was called a phase change diagram. Well, the diagram part means it's something visual, it's a graph, and phase change means it's pointing out that a phase change of melting and the phase change of boiling requires some amount of extra energy. So what's the deal with the extra energy we had to put in? Well, that's referred to as latent heat. Latent is an old-timey word that means hidden or secret or unseen. So we call it latent heat because scientists didn't originally know what this extra energy was doing. Extra latent heat, it turns out, must be added in order to change from one phase to another. So you need to put extra latent heat into a solid to turn it into a liquid, and you also need to put in extra latent heat to turn a liquid into a gas. Finally, the most important thing you can learn from this phase change diagram is visually you can see that during a phase change, temperature does not increase. When the solid was melting, it started at 0 degrees as solid and ended as still 0 degrees, but liquid. And same thing up above. We talked about how this part of the plateau is 100 degree liquid, and this other end is 100 degree gas. So temperature does not change when you're doing a phase change. It's either one or the other. You're either increasing in temperature or you're changing phase. So we'll keep that in mind as we go forward and look at more phase change diagrams. Here's one that helpfully shows up at the top a visual of what's going on in the molecules during these 5 parts of the graph. Over on the left, we have the section that represents the solid molecules as they're being heated up from low temperatures to high temperatures. Then we get to this plateau, and again, you'll be able to memorize pretty quickly that a plateau means a phase change. So this first phase change is the solid turning into a liquid. So looking up at the top, we can see we'd get kind of an icy mix here, almost like a slush of solid mixed in with liquid. And over on the left of that section, it's all solid, and over on the right, it's all liquid. Then in this section, we see the liquid getting hotter and hotter and hotter. Then at this phase change, at this plateau, we see the liquid boiling into a gas, and again, we have kind of like a misty combination of liquid and gas here. When we get to the end of that plateau, 100% of the liquid has turned into gas, and then the gas can just heat up as pure gas for as long as it can. And that's pretty much what phase change diagrams will always look like. The only things that will change from one diagram to the next is what the numbers are on the axes. Remember that we've been talking so far just about H2O, just water, and that's still what's being reflected in this diagram, because if you look over on the side, it shows 0 degrees as the melting or freezing point, and it still shows 100 degrees as the boiling or condensation point. So this must still be referring to water. But for other materials that are not water, these numbers will be different, and eventually you'll even see phase change graphs that have numbers on the x-axis. But for now, we're just simplifying. Okay, so that's what a phase change diagram is. But in order to use these effectively, you're going to need a little bit more information. We're going to talk for a moment about latent heat in these 2 phase changes of melting or freezing and boiling or condensing. The 2 terms you're going to need to learn are latent heat of fusion and latent heat of vaporization. You can see we changed from the word fusion to vaporization, but otherwise it's going to be the same concept for those 2 sections. So let's talk about those. Latent heat of fusion means the amount of thermal energy that must be absorbed or released by a substance at its melting or freezing phase change. That's a really heavy definition. Let me give you a simpler version of that, a less textbooky version. Latent heat of fusion is simply the energy that you need in order to accomplish a solid to liquid phase change or a liquid to solid phase change. You can go in either direction and it's going to be the same amount of energy. And you're either going to take in that energy and turn from a solid into a liquid, or you could give up that amount of energy and go from a liquid to a solid. So latent heat of fusion is the energy needed for this kind of phase change. There's an equation that goes along with latent heat of fusion, and it looks like Q equals M times HF. Q always represents how much thermal energy is being transferred from one place to another. So I've highlighted in the diagram that the Q in this case is the heat energy coming from the fire going into melting the ice. And the way you would calculate how much latent heat is required to make this happen is M times HF. M stands for mass, because if you have a large ice cube, that will require more energy to melt than a small ice cube. And HF is a new special term for us. It stands for heat of fusion, and what it means is the amount of joules of energy that are needed in order to change 1 gram of a solid into 1 gram of a liquid. Now, it would be nice if this was a constant that we could plug in, like it's always the same number, but unfortunately it's actually a different number for every substance in the universe. So you wouldn't be able to guess what that number is. Instead, you'd have to either look it up in a data table, or your teacher would have to come out and tell you what the value of HF is. We've now been talking about latent heat of fusion. Let's now talk about latent heat of vaporization, which is the other one. Luckily, this is the exact same idea, just for a different moment in time. Latent heat of vaporization is the amount of thermal energy that must be absorbed or released by a substance at its vaporization or condensation phase change. This is the exact same definition as latent heat of fusion, but I've switched out the bolded words. So now instead of the lower phase change, we're talking about the higher up phase change. Latent heat of vaporization is usually a bigger amount of energy. You need lots and lots of energy to turn a liquid into a gas. Once again, here's the simple version of this definition. Latent heat of vaporization is simply the energy that you need in order to accomplish a liquid to gas or gas to liquid phase change. If you're a liquid and you want to become a gas, then you need to take in that much latent heat. But if you're a gas and you want to go down to become a liquid, you need to give away that much latent heat. But it's always the same amount, no matter what direction you're going in. Here's the formula for calculating Q, which is the latent heat you have to add or subtract, equals M, which stands for mass, once again, multiplied by HV. And I bet you can figure out what that stands for. That stands for heat of vaporization. And just like HF, heat of fusion, HV is also a number that you would have to either look up in a data table or be told outright by your teacher because it's a different value for each substance. So again, heat of vaporization, or HV, is the number of joules of energy that you need in order to change 1 gram of a liquid into 1 gram of a gas of the same substance. Okay, now that you've learned these two new formulas, you're actually prepared to start analyzing full phase change diagrams. This is the same diagram as before, only beneath the labels for what each section represents, I've also added the equation that you would use if you wanted to calculate how much heat energy would be required to do each of these steps. So if I want to know how much heat energy is required to take a negative 40 degree block of ice and turn it into a 0 degree block of ice, which is very much the kind of question you'll be asked in this unit, then you can simply say that the change in temperature was 40. The specific heat capacity of ice is a number that you would just plug in from a data table, and then the mass of the ice you could plug in as well. You'd usually be given that information in the question. And that would calculate Q. You probably already know the equation Q equals mcΔT from a previous video. But now if that ice cube gets warmer and then reaches its melting point, now you could also calculate how much energy would be used to completely melt the ice into a puddle of water. Then, once all of the solid has turned into all liquid, you could go back to your original equation and start using it again, because now we're dealing with a temperature change, so we use the equation that deals with change in temperature, delta T. Once we reach this higher temperature at the boiling point of a substance, you switch back to using the phase change equation. And the lower phase change uses HF, and the higher one uses HV, but otherwise it's the same type of equation. So there's really only two types of formulas. There's temperature changes, which uses mcΔT, and there's phase changes, which use M and HF or M and HV. Finally, once all of this boiling has occurred and you've calculated how much heat is needed for that, then you can take this gas and make it as hot as you want and calculate how much energy would be needed to do that. So the most amount of steps you would have in a problem like this that deals with a phase change diagram is 5 steps, because the cold solid might warm up and then melt, and then the liquid might warm up and then boil, and then the gas might heat up. But you won't go any farther than that because we don't deal with plasma, which is kind of the next step here. And a solid can get colder and colder and colder, and it will just stay a solid. So there's no real plasma equivalent on this side to even start to talk about. So that's phase change diagrams. And now that you've seen all the concepts, it'd probably be a good idea to practice it. So there's just going to be one sample problem in this video, and here it is. How much total thermal energy must be added to 125 grams of solid ice at negative 17 degrees Celsius in order to turn it into liquid water at 40 degrees Celsius? All right, now this problem is really heavy. There's a lot going on. You would actually need to solve this problem in 3 steps. There's not a single formula that can get you the answer you're after. The first step is going to involve heating up the solid until it reaches its melting point. Why would we do that? Well, remember that we're starting out with a solid block of ice, and it eventually turns into liquid water. So there's going to be a phase change at some point where the solid becomes a liquid. That can only happen at the melting point of this substance. So the first amount of energy, or Q, that we're going to have to calculate is the energy required to heat up the solid to its melting point. The next step is figuring out how much energy is required to then melt the solid into a liquid. We already got it to its melting point, now it needs to do the actual melting. That's two separate steps, and they're going to use two different equations. Finally, once the solid has melted into a liquid completely, we then need to get the liquid up to its final temperature, which in this problem they say is 40 degrees. Now that's above the melting point of ice, so there is going to be some final increase in temperature there. Now, in my opinion, these three steps are going to be much easier to understand if you can visualize them. So here's a phase change diagram, which we've just been learning about. You should be able to recognize the 5 sections of a phase change diagram. The first slanted section is the solid heating up. The first plateau is the solid melting into a liquid. The next slanted section is the liquid heating up. And even though we're not going to do that in this problem, the next plateau would be boiling, and then the final slanted section is the gas getting hotter and hotter. This is just a 3-step problem, but it could be up to 5. Okay, so the first thing we need to figure out is how much heat is needed to take the solid ice from negative 17 degrees to its melting point, which would be at 0 degrees. So here's the first formula I would use. Q number 1, which would be the energy required for part 1, is equal to mcΔT. Again, M stands for mass, C stands for the specific heat capacity of the material, and delta T means the change in temperature. Usually it means the increase in temperature. So one thing that I've changed here is instead of just saying C for specific heat capacity, I'm saying C solid. Why am I saying that? Well, it turns out that ice actually has a different heat capacity than liquid water does. And this is not super uncommon. You'll see what I mean in a second, but the amount of effort you have to put into heating up ice is different than the amount of effort you need to put into heating up water. So we'll see how those numbers work out in a second, but first let's just carry on to what equation will be used for step 2. Step 2 involves melting, and so that's a phase change, so we would use this formula. The amount of heat energy needed to melt the ice would be M times HF. Again, M is the mass of the ice, and HF is the heat of fusion of ice. That's something we'd look up in a data table, just like we would look up the specific heat capacity on a data table as well. And finally, the third step involves heating up the liquid that we've made from its original melting point to its final temperature. That would be going from 0 degrees Celsius to 40 degrees Celsius. That's a temperature change, so we must use the formula that has a change in temperature in it, or delta T. So therefore, the equation we would use is Q equals mc delta T, which is the formula that we always use when something is changing temperature. You'll notice here that I've written that this is going to be the specific heat capacity of liquid water, because as I mentioned before, ice and water actually have different amounts of effort you have to put into heating them up, because they have different chemical structures. You would once again look this up on a data table. You wouldn't need to know it yourself from the problem. So that's how these 3 steps will be calculated. The very last step that we'll do is adding up all 3 of our answers, because the question asked how much total energy must be added to this ice to turn it into water at this temperature. That involves 3 steps, so we need to calculate all 3 and then put our answers together. All right, here's our math. Q1, the energy required for step 1. That would be the mass of the ice. In the question, they said it was 125 grams. Then we need the specific heat capacity of solid ice. From a data table, you could find out that that's 2.09 joules per gram degree Celsius. It's an awesome unit right there for specific heat capacity. And the change in temperature at this first phase, remember that it goes from negative 17 to 0? Well, that's an increase of 17. So for our delta T, we plug in 17 degrees Celsius. We could put all those numbers together in our calculator and get an answer of 4,441.25 joules of energy. That's how much energy is required to do just this first little step right here. So that's how far we would walk on the x-axis. That's how much Q we add going from here to here. Stage 2, here we go. The heat energy needed to melt the ice into water. M is still 125 grams because we're still talking about the same ice cube as before, so mass is not going to change here. And then the heat of fusion of ice, we would look up on a data table, and we'd find that it's 334 joules per gram. So in other words, you need this many joules of energy to turn 1 gram of ice into 1 gram of water. Putting those numbers into our calculator, we get that it takes a staggering 10 times almost the amount of energy to melt that block of ice as it took to just raise its temperature a little bit. So clearly, the amount of energy that it takes to phase change is not an insignificant number that you can just ignore. You have to account for that, or your answers are going to be way, way off. So we have this answer for how much energy is required for step 2. Great, let's do our math for stage 3. Once again, we're using Q equals mc delta T. The mass is again 125 grams. But now the specific heat capacity of the liquid version of water has to be used, because on your data table, you'd actually find that it's 4.186 joules of energy that are required to take 1 gram of water and make it 1 degree warmer. That's the specific heat capacity of liquid water, and that's different from ice, which was 2.09. So there's a lot of details to get from your data tables here. Finally, the delta T. Well, this is the third part of the graph where it's going from 0 degrees to 40 degrees. So obviously that's an increase of 40, so that's our delta T in this case. That's the increase in temperature. Putting these numbers in our calculator, we get this answer, 20,930 joules. So let's finally put all those answers together, and we get a total of 67,121.25 joules. And you could also answer in kilojoules if you want to, in which case it would be about 67.1 kilojoules, because again, kilo means 1,000. So that would be your final answer. And this is a pretty big problem. You could very easily get a test question that involves this many steps. So you want to make sure you're really familiar with which equation you use and when on a phase change diagram. If you're feeling a little bit intimidated by the amount of math that I just did, don't be, because all I had to do was just figure out what equation to use for these 3 sections, and then simply plug in numbers either from a data table that my teacher gave me, or plug in numbers from the problem, and I got 3 answers, and I put them together at the end. That's all I did. So when you practice with this, you'll get really good at it, and it won't seem as intimidating anymore. So you'll be feeling pretty good about it in no time. So that's pretty much everything you need to know about phase change diagrams. To summarize, remember that a phase change diagram is a graph that tells you the story of what happened to the temperature of a substance as you were adding heat energy to it. We learned in this video that solids, liquids, and gases will change temperature as you add heat energy to them, and you can calculate how much their temperature is going to change, or how much mass they have, or what their specific heat capacity is, or what heat energy is required by using this equation. But then when they're going through a phase change, you have to use a different set of equations, which is m times hf, or m times hv. So if you're asked a really short physics question about one of these sections, make sure you pick the right equation. And then if you're asked a multi-step question like the one we did, make sure you first identify what sections of the graph your substance is experiencing, and then select the right equations for all those sections, and then put your answers together at the end. So I hope that was helpful, and I'll see you in the next video. Bye.